Thank you, Rachel. Again, I'm Raquel Martinez, aka ASAP Rocky Planet, and I'm a Harrington Graduate Fellow here at UT Austin, and I just finished my second year in the Astronomy program PhD, PhD program. And I'm here to talk to you about actually the radial velocity method of exoplanet detection, but in layperson's term, I'm going to tell you about finding exoplanets with wobbling stars. And so, as many astronomy history stories begin, it all starts with an old dude. So here's Johannes Kepler, and in the early 1600s, he came up with 3 laws that described how the planets in our solar system orbited around the sun. So there are 3 laws, and the first one says that the orbit of every planet is an ellipse with the sun at one of the 2 foci. The second says that a line joining a planet and the sun sweeps out equal areas during equal intervals of time. And the third says the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. Now, the 2 laws that are most important for finding exoplanets are outlined here in red, but let's put some pictures to these words. Okay, so here is a little geometry refresher for you all. We have an ellipse here outlined in blue, and then as the planet orbits the star along this path, the 2 foci are, one is occupied by the star that the planet orbits, and then the other one's just out there all alone, being all lonely and stuff, and empty. And then every ellipse is described by its eccentricity, so that's basically how oblong the orbit is, and then also its semi-major axis, which is equal to half the length between the 2 most distant points of the ellipse. And so it's demarcated here with an orange bar. Now skipping over to Kepler's third law, when students are first introduced to it, they're usually shown this expression, p squared goes as a cubed. So p represents the period, or the time the planet takes to go around the star once. And then a, again, is the semi-major axis, cubed. And what I find really fascinating about this expression is that Kepler actually determined this proportionality by just looking at the 6 known planets at the time: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Next, another old dude. This is Sir Isaac Newton, and he was actually able to pinpoint the exact, to turn this proportionality into an exact expression using his law of universal gravitation. So we have p squared equals 4 pi squared a cubed, so that a is the semi-major axis and the p is the period again, and then we have this big fancy g. Here's the gravitational constant, and it's also inversely proportional to the total mass of the system. So what Newton did was introduce a subtlety of that the planet is not orbiting a stationary star, but since the planet and the star are gravitationally exerting forces on each other, the total system is actually orbiting a common center of mass. And so that generalized things tremendously, so that we actually can now expect stable configurations of vast different kinds of systems. And so here we have an equal mass binary system orbiting a center of mass, their center of mass in a circular orbit, but we can also get stars that are unequal in mass orbiting. This here is a circular orbit, but they're just of unequal mass. And then we can also get things like this that are pretty funky, where we have the 2 equal mass stars, but they're orbiting on very eccentric orbits. Now let's fast forward another 300 years and think about something that another old dude considered. This is actually someone that has major ties to Texas. This is Otto Struve, and he was the founding observatory director for McDonald Observatory, so Hookham. Having armed with the knowledge that Kepler and Newton gave us, and realizing that the spectrographs, or the astronomical instrumentation that we have, was good enough that we should be able to detect the wobble of a star being influenced by the pull of the gravitational pull of a planet orbiting it. And so in 1952, he wrote in an article proposing this idea, a proposal for a project of high precision stellar radial velocity work, and in it he stated that, this is in 1952, that it should be possible without much difficulty to discover planets 10 times the mass of Jupiter by the Doppler effect. And now, what the heck is that Doppler effect? Some of you may have forgotten, some of you probably still remember what it is, but if you forgot, I'm going to explain it, or someone's going to explain it to you.
Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
So you guys all get it, right? I don't have to explain it anymore. Well, just as Sheldon said, the Doppler effect is the apparent change in the frequency of a wave caused by the relative motion between the source of the wave and the observer. And many of us have experience with this on a regular basis when the sirens of ambulances and fire engines come towards us and pass us. And so as the siren comes towards us, the sound waves are compressed into a smaller distance, and our ears perceive that as a higher frequency or a higher pitch. As the siren goes away from us, the sound waves are over a larger distance, and so we perceive that as a lower pitch. The thing is, Otto Struve wasn't telling us to try and hear the wobbles of the stars. He was actually trying to tell us to see the wobble of the stars. So, as we remember, the planet star system, so this is just, imagine this one and this one are in orbit. And so they're orbiting the common center of mass. And so as the planet's motion along our line of sight, or its radial motion, goes away from us, that exerts a pull that brings the star towards us along its radial motion is coming towards us. And just like the sound wave got compressed, the radiation from the star gets compressed, so its frequency is increased and its wavelength is shortened, and so we say that the radiation from the star is blue shifted. And then as the planet goes around in its orbit and its radial motion is towards us, that means that the star's motion is away from us, and so the radiation wavelength is increased and its frequency is lowered, and so we say that this radiation is redshifted. And I wish I could tell you that when we look through a telescope we see blue and red sine waves, but that's not actually what happens. What we need to do is figure out a way to figure out what the light, we have to disperse the light, just like a prism does. So we attach these instruments called spectrographs onto our telescopes that are able to disperse the light just like a prism does, and so we can see the different components of the light within it. And then what we see is that there are these small deficits in intensity, here, here, and here, for example, that actually is, that's material in the star's atmosphere. And so as photons try to escape from the center of these stars, they encounter these elements and ions that actually absorb those photons, and they are not allowed to escape at particular wavelengths that are actually very well known. So if we have a good idea of what the star's spectrum is at rest down here, we can observe the stellar spectrum and determine, based on the discrepancy between the observed spectrum and the spectrum that's at rest, we can convert that into a radial velocity. And so we keep on observing the star to try and sample the orbit as much as possible. And so we try to sample it as much as possible. Therefore, we look at it for days, weeks, months, even years, and then we look at the radial velocity trends to see if the radial velocity, or RV, is periodically changing with time. So from 1952, fast forward to 1995, and then we found the first RV planet, 51 PegB. And so actually, a few years prior to this, we had actually found exoplanets around neutron stars, but this was a really exciting discovery because this was the first planet that we were able to find using the RV method around a normal main sequence star. And what was really crazy about this planet was that it was half the mass of Jupiter and orbiting its star in 4 days. So that was crazy. And so this is just a plot of the star's radial velocity motion as a function of where it is in its orbit. And we are seeing that we're detecting about the star moving away from us at about 50 meters per second at its highest, and then coming towards us at about 50 meters per second. And so the fact that 51 PegB was this hot Jupiter, a massive star, a massive planet, very, very close to its host star, it opened the floodgates, and many astronomers wanted to try and find more and more of these planets. And so we experienced this boom, and here's just an example of the things that we found. Here we have some pretty extremely eccentric systems, but also taking a look at the y-axes on these RV plots, what you're seeing is that it's getting pretty huge range to very, very small. So what this is telling us that as time goes on, our instrumentation was getting better, and then we were able to find less massive planets orbiting their stars because they were exerting such a smaller force on their host star. So just to give you an idea of like how crazy sensitive these observations were. So imagine that these systems are many, many light years away, and these planets are billions to 100 billion meters away, and they're influencing their stars on these small velocity measurements. And so in the 1950s, when Otto Struve suggested that we should be able to find these, the spectrographs were as sensitive to find radial velocity measurements as low as 100 meters per second. Now, in 1995, and this is just, I did these calculations, so this is actually what we are detecting. In 1995, for 51 PegB, the spectrographs were sensitive to find the motions of the stars at 10 meters per second. Today's RV spectrographs are able to detect motions in the stars at 1 to 3 meters per second, and hopefully in a few years we're going to get down to 10 to 20 centimeters per second. And this is really important because the Earth's influence on the sun is about 9 centimeters per second. So if we want to find Earth-mass planets orbiting at Earth-like distances, we need to get below this 10 centimeter per second precision level. So here is just what happened after finding 51 PegB, and the red is the radial velocity. So after 51 PegB, radial velocity method was the way to find exoplanets for astronomers. And then we have these two huge pesky spikes over here from that Kepler mission finding all those planets with a transit method. But before this year, you actually still needed to vet any Kepler candidates with an RV-based RV detection to turn those Kepler candidates into bona fide planet, confirmed planets. And so what kind of planets were we finding? Here's another plot that shows the planet mass of the planets found through the RV method as a function of discovery date. And as you can see, as time marched on, we were finding smaller and smaller massive planets. And so these are just, you know, the planets in our solar system for scale. And so we're right about getting those an Earth mass planet with the RV method. And then here is a plot that shows you the architectures of the planets that we were finding with, of the planetary systems that we're finding with the RV method. And as you can see, so we have Earth here, this is where we are on this plot, and we aren't there yet, but hopefully in a few years we'll be able to march this detection limit down and be able to find systems that house planets that look like ours and are situated like ours. So with that, I'll thank you and I'll welcome your questions.
All right, thank you very much, ASAP Rocky Planet. I got it, yeah. We got time for a few questions. We'll start second row here.
Explain in layman's terms statistical methods that were used to confirm the Kepler planets.
I'm actually leading a research discussion on this tomorrow, and I haven't read the paper, but I know I should have done it sooner. So it's a machine learning type of thing, and so they have like a training set of data where they know what a planet is, and they know what not a planet is, and they figure out the characteristics that differ between them. And so when they do this, you know, if they have a bunch of different kinds of characteristics, then they just multiply those probabilities to have a certain idea of whether it is a planet or it is not a planet.
What's the for me.
Is that good?
All right. I will take one question from Twitter real quick. Can't talk tonight. How do you tell the difference between the light of 2 stars versus 1 star when you're observing them for this method?
Between 2 stars. Well, so like you'll be able to see if there's 2 stars that you can actually see their spectral lines. Then as you track the different the orbital motion as you keep sampling the orbit, you might be able to actually fit 2 sine curves to that star and actually get the different orbits for the different stars at the same time. Yeah, I think that's that's the best I can do.
Works for me. Right here.
Yeah, so the ones that I was showing you were very so if it's a very circular planet or a circular orbit, you'll see a very sinusoidal RV signal. But if there's like a slight deviation to it, you might be able to introduce another planet into the system that accounts for that deviation from the single planet solution to the problem. And so there are ways to just like, let's inject another planet. So how many planets do we need to inject to reproduce the RV signal that we get? And you can get like a statistical confidence of whether adding another planet gives you a better fit to your RV data.
All right, you seem very eager.
Oh, so the transit method is if so the planets are just like aligned, willy-nilly out there. It's just a probabilistic thing. But like on the chance that the orbit is inclined so that what the planet crosses in front of the star as from observed from Earth, then we'll be able to see a tiny dip in the brightness of the star. And so if that has a periodic signal, then we can say, oh, there might be a planet crossing in front of that star. I don't say that they're better or worse. They just have different parameter spaces that they probe. So we might be able to find closer planets or more massive planets or whatever. Whatever's your favorite kind of planet, there's probably a detection method out there for you.
All right, let's look upstairs. Do we have anybody upstairs or on the stairs? All right up here.
How are we getting down to the 10 centimeter per second plan?
Ooh, I want to know that too.
You want to? I'm not an instrumentationist, but so basically you need to have one way to you need to really calibrate your stellar spectrum. So the detector that you have needs to be very, very stable. You need to really know the wavelengths very well. It's just like trying to exclude all the noise that you can introduce when you're actually observing. That gets you down to it. But that's as good as I can tell you. Explain it right now.
All right, one more question right up front.
How do you observe it?
How
What is the instrumentation?
How do I so?
What is the instrumentation for observing that effect?
The radial velocity effect, or what is the so we have the telescope. We put the spectroscope on it, spectrograph, and then we have the CCD.
Okay.
Yeah.
All right, one more question. That was a quick one. Right back here, standing.
That's a good question. Can you repeat the question for me so I can repeat it for everyone?
It's the work of the, quote, Harvard computers, the women who did stellar photography in the early 1900s, and Henrietta Swan Leavitt, who worked out that you can measure distance by way of Lucius redshift, influenced the work.
So that's a little bit further out. So the RV detection method is more of a closer way of detecting planetary systems. Her work was necessary for basically figuring out how far away things are outside of our galaxy.
All right, one more quick question since we've had lots of quick answers. I like your efficiency.
Oh, sorry.
Well done. Right here, last one, I promise.
Since you're measuring Doppler shift, won't the orientation still matter? And so in other words, if it's tilted,
So-
it's going to measure different red and blue shift than if it was aligned.
Exactly. So basically what we're actually, the RV is just the motion of the star along our line of sight. So the masses that we get out of it aren't necessarily the true masses of the planets. They're actually the minimum mass of the planet. And so if we're lucky enough to detect an RV planet and then it happens to transit, then we can actually narrow down that inclination even more to actually get a more robust measurement for its mass. But yes, you're absolutely right. I kind of glossed over that because I only have a few minutes to give a talk.
Fair enough to gloss over that. All right, let's thank ASAP Rocky Planet one more time.